In this case of the thermochemistry, in lecture 9, I shall discuss the enthalpy of combustion and the bond energy. Both the terms are very useful in chemistry, and the enthalpy of combustion is denoted by del Hc. It is the amount of heat change associated with complete combustion of 1 mole substance in excess oxygen, and whenever the standard enthalpy of combustion we can call, it is denoted by del Hc naught. Here C is the combustion, H is the enthalpy, del means difference, and naught is indicated when all the reacting components are in their unit activity, or if the gases are there, then 1 atmospheric pressure, and the temperature is preferably 298 Kelvin unless otherwise stated. So I can set some examples of this enthalpy of combustion. It is the heat change at a constant pressure for the combustion of 1 mole of the substance, complete combustion. So the thermochemical equations of combustion of some different compounds, of some different substances are given here. Number 1, CH4 gas plus twice oxygen gas and giving this carbon dioxide gas plus twice water liquid, and del H naught C for CH4 gas. This is the compound, and it is equal to minus 212.80 kilocalorie per mole. It means that if 1 mole of gaseous methane is undergoing the complete combustion in excess of oxygen, then these are the products obtained, and this amount of heat will be liberated. So in case of 2, suppose carbon solid plus O2 gas and giving this carbon dioxide gas, and in this case del H naught C of this carbon solid is equal to minus 94.05 kilocalorie per mole. And this third one I can also write, this hydrogen gas plus half oxygen gas and giving this water liquid, and the LH standard enthalpy of combustion for this hydrogen gas is equal to minus 68.3 kilocalorie. Another example I can also cite here, the nitrogen gas plus oxygen gas. Nitrogen is undergoing the complete combustion with oxygen, giving this nitric oxide gas, and in this case del H naught C for this nitrogen gas is equal to minus of plus 43.2 kilocalorie per mole. So these are some examples of this standard enthalpy of combustion of these different substances. And I can also give one hint that hint is that the standard enthalpy of combustion is very easy to determine experimentally. And this is why this heat of combustion or the enthalpy of combustion is used for some theoretical purposes. It is used to calculate the standard enthalpy of formation of a substance, which is not possible to determine experimentally. One example I can say, applications I can give here. Suppose formation standard enthalpy of formation of a methane gas. According to the definition, the reaction will be C solid graphite plus twice H2 gas and giving this CH4 gas. And the delta H naught F of this methane gas is not known now. As this reaction is not possible to do in a plant or in laboratory, so this one is not known to us. And by the heat of standard enthalpy of combustion, it is possible to calculate the standard enthalpy of formation of this compound, though this reaction is not possible to conduct. If it would be possible to conduct this experiment, then we can get this easily, the methane from this carbon and hydrogen, carbon from coal and hydrogen from this water gas. And you know, the methane is the starting material of so many medicines, and also it is used as a fuel. So this one we can get it by using some mathematical operation, and the mathematical operation is that say equation 2, this is the mathematical operation, so we are doing plus 2 into this equation 3 and minus the equation 1. If we do this mathematical operation, then we shall get this reaction carbon solid plus twice hydrogen gas and giving this CH4 gas. And del H and del H naught F of this CH4G is equal to this one too, means minus 94.05, all are kilocalorie per mole. This value, and then 2 multiplied by 3 means plus 2 into, and in case of 3 the standard enthalpy of combustion is minus 68.3 and minus this one is minus 212.80, and moles are cancelled, moles will be cancelled and it will be kilocalorie. So if we do this problem, and then it will give this minus 17.85 kilocalorie per mole. So this standard enthalpy of formation of this methane we are getting here, this is equal to minus 17.85 kilocalorie per mole. So this is one good application for the calculations of this enthalpy of formations. I can give here one home task or homework to do. Homework. Calculate the enthalpy of formation of ammonia gas given the enthalpy of combustion of ammonia and hydrogen as minus 90.6 kilocalorie per mole and minus 68.3 kilocalorie mole inverse respectively. This answer is minus 11.85 kilocalorie mole inverse, and the reaction you do this problem at your own home and practice how this enthalpy of formation of a compound could be obtained from this enthalpy of combustion. Enthalpy of formation could be obtained from this enthalpy of combustion data. Not only that, the enthalpy of combustion, or you can say the standard enthalpy of combustion, have different applications. First applications, I can say theoretical one, theoretical application. And I have done in the case of calculation of the standard enthalpy of formation of a compound. And another application is the standard enthalpy of combustion will be utilized to calculate the Bohr energy of a compound. And second one is a practical application. Practical applications. And practical applications of this enthalpy of combustion is also very important. A purchaser of coal, or I can say the coal purchaser, will try to take that type of coal whose heat of combustion is the largest one per ton. He is interested with this enthalpy of combustion or heat of combustion per ton of this coal. Greater the value of this heat of combustion of this coal, or greater higher will be the quality of that coal. Not only that, dietitian also being interested to find the enthalpy of combustion or heat of combustion of different foods, and so that the dietitian can prescribe how much calorie of heat the person can consume. And in case of nutrition, one thing I can say, this calorie, big capital C, calorie means kilocalorie per mole. Kilocalorie per mole. So, I can outline a simple method to determine the heat of combustion of a substance. It is done in a bohm calorimeter, means constant volume. The enthalpy of combustion, heat of combustion is determined, and this is like that one. And this is the bohm calorimeter. See, I am giving just giving one outline, and here the pressure tight screw cap, and this is of capacity. Capacity of this bohm calorimeter is about 400 cc, and it is filled with sufficient oxygen at about 20 to 25 atmosphere. Here actually given one spoon. This is the spoon, in which the substance, a definite amount of this substance, is taken, whose heat of combustion we like to determine. And here one connection is there, electrical path, and this one is platinum, this enamel internally, this one is internally enameled with platinum. And this one is immersed in water. Here is the thermometer. One thermometer is inserted also here. And whenever this spark plug is conducted in a battery, there is a spark and ignition of this. Suppose here 1 gram or some amount of carbon is taken. Say 1 gram carbon is taken in this spoon, and this carbon is ignited through this spark, and the large amount of heat will be released by the combustion of carbon with oxygen, giving this carbon dioxide, and the temperature of this water bath will also be increased. So this temperature is measured by means of this thermometer, and if the total heat capacity of the system is predetermined, then it is daily heat of combustion at constant volume will give you the amount of heat, the heat capacity of the system into temperature rise of this bath divided by amount of the substance taken in grams divided by molar mass of the substance. So once this delta U is known, heat capacity, temperature rise, and whenever this one is the heat of reaction at constant volume, and if we like to get this delta H, then delta U plus delta Ng and RT. So by this way, this one, the enthalpy of this combustion of carbon is obtained. Now I am coming to this bond energy. The bond energy is defined as the bond energy of a given bond is defined as the energy, average energy required to dissociate the said bond present in different gaseous substances, gaseous compounds, into free radicals or atoms in this gaseous state. These underlines are to be taken very carefully. And this bond energy differs from this dissociation energy. Dissociation energy, not the average energy. Dissociation energy is the energy required to dissociate a particular bond in a specific compound. but in this case it is the average energy considering the different compounds in which this said bond is present, and the compound and the dissociated products are all in gaseous state. I can give one example. Say for the case of water, this water is taken as this H and H, and it is in gaseous state, and giving this OH plus H. And suppose this is also in gaseous state, and H, the atom, free atom, is also in gaseous state, and this is the free radical. And del H naught 298 Kelvin equal to, suppose 100, 120, 100, 190, 119.95 kilocalorie per mole. It means that if we like to dissociate this OH bond into this free radical in gaseous state and this free atom in this gaseous state, this amount of energy will be required at constant pressure for dissociate 1 mole of this water. And second, suppose this OH in gaseous state and giving this O, free oxygen atom and free hydrogen atom, and in this case delta H naught 298 Kelvin will be of different value, and this value comes up, suppose 101.19 kilocalorie per mole of this compound, per mole of this bond to be broken up, and this amount of heat at constant pressure will be required. So this bond actually depends on the other part of this molecule with which this bond is associated. So this is why the difference of this magnitude is coming. So the average value of this OH bond equal to half into this 2, means 109.95 plus 101.19, and this will give you this 100. This will give you the 110.57 kilocalorie per mole. If we like to very good value of this bond energy of this bond OH, then we shall have to consider the different bonds present in different molecules. Say, suppose here it is the phenol, here OH, and it is gaseous state, or some other compounds, say CH3, OH, or many compounds to be taken, and dissociation energy for this particular bond is to be determined, and the average value will give you the more accurate bond energy of this particular bond. And this bond energy would be given in a table of a textbook at 25 degrees centigrade in kilocalorie per mole. and the bond energy actually would be determined. Bond energy would be determined from this enthalpy of combustion. Enthalpy of combustion. This is another important application of this enthalpy of combustion. Suppose we like to consider this CH4 gas, and this is actually 4 bonds are there. So carbon's gas plus 4H, this is also gas, and delta we like to calculate the standard the enthalpy change for this process, and the enthalpy change of what we can obtain for this reaction, it is to be divided by 4 to get this bond energy of CH, as this 4 CH bonds are associated with this methane. So this will give you this 1/4 and into a del H naught and combustion for CH4 and G. Let us get a scheme how to this value would be obtained. This value would be obtained. Now I set one example how this bond energy of a particular bond would be calculated by the use of this enthalpy of combustion data. Suppose we like to calculate the bond energy of CH bond. So this bond actually is methane in the gaseous state. It contains this 4 CH bond, dissociates into carbon gas and plus a 4H gas. This is the subcompound in gaseous state, and these are the products. They are also in gaseous state. And what will be the enthalpy change? Standard enthalpy of this reaction divided by 4 will give you the bond energy of CH. Means CH equal to 1/4 of this heat of combustion of this enthalpy of enthalpy change, standard enthalpy of this reaction. So what we can do to get this value? Actually, these are the steps we have to take up. One is the methane gas undergoing combustion, carbon dioxide, water, and this is the heat of combustion of methane. And this one, carbon dioxide, here carbon dioxide is there. Carbon dioxide is to be eliminated. Carbon dioxide is decomposed to carbon plus oxygen, and the enthalpy change at standard enthalpy change at 298 Kelvin will be equal to the reverse of the standard enthalpy of combustion of carbon. So this is plus 94.05 kilocalorie. And if we consider this twice water, twice hydrogen gas, so this is also the reverse process of the combustion of 2 moles of this hydrogen. So this will give you 2 into 68.32 means this kilocalorie amount of heat will be required to dissociate the 2 moles of water liquid. Water is to be eliminated. 2 moles of water is to be eliminated from this reaction. Then this hydrogen, 2 hydrogen molecule, and giving 4H gas, and this is the process of atomization of this molecule. and in this case it is 2 into 104.1, 104.19, and this is this much kilocalorie. This one is the atomization, heat of atomization or enthalpy of atomization for 1 mole of hydrogen gas. So it is 2 moles, 2 is multiplied. And the carbon solid, this carbon solid is to be converted into gas, and this is the process of sublimation. And the amount of enthalpy change, standard enthalpy change at 298 Kelvin is also equal to 171.29 kilocalorie. If you sum up all these values, then you can see carbon dioxide cancels, this water cancels, and this hydrogen is cancelled, this carbon and this carbon solid cancels, and 2 oxygen, here 1 oxygen, another oxygen, all are cancelled, and leaving this residue as CH4G, and here the C gas and 4H gas, and this value is the standard enthalpy of this reaction at 298 Kelvin. So this bond energy of CH will be equal to 1/4 of this value, and it is 99.4 kilocalorie per mole. So by this way, the bond energy is calculated from this enthalpy, standard enthalpy of combustion. So to get this accurate value of this bond energy, we shall have to use the different compounds containing this CH bond, and we shall have to take this average value. And one utility I can say here, utility or applications of this bond energy. Applications of this bond energy is of prime importance, though this value, calculated value from this bond energy will be approximate 1. Say suppose we like to get this enthalpy, standard enthalpy of a reaction. Standard enthalpy of a reaction. Suppose del H naught 298 Kelvin. So suppose this is the reaction CH4 ethylene in gaseous state plus HCl, this is also gaseous state, and giving this C2H5Cl, this is also gaseous state. If we like to apply this bond energy, say apply this standard enthalpy at 298 Kelvin of this reaction, then we shall have to be restricted that all the reactions and products all are in this gaseous state. So in this case, and also we know the structure of this compounds, reactant and products structure must also to be known. And here actually 4 CH bond is there, and del H naught 298 Kelvin equal to, suppose this is to be determined, then energy required to break the bonds, present in the reactants. This is one thing, reactants, and minus the energy plus energy released when the bonds are formed in the products. So in this case, it will be 4CH, 4 bonds are to be broken from in this compound. Plus 1 epsilon C double bond C, and in this case plus epsilon HCl. All are in gas state. These are positive, means the bond energy is required. Minus here this plus, here minus 5 bonds are there, 5 CH bonds are there, and minus 1 CCl bonds is also here, and we should know the structure. Here the structure is C double bond C, and here H, and this 4 CH bonds, and in this case HCl, and giving this C single bond, plus here is 1 single bond, 1 epsilon CC, and minus 1 epsilon CCl. And in this case, here it is Cl, here H, here H, here H, and the 5 CH bonds are there, 1 CCl bonds and 1 CC single bond. If we put these values, let us simplify. These are negative, means energy released. These are positive, means energy is required. If we simplify, then it is epsilon C double bond C plus epsilon HCl, and minus this one minus 1 epsilon CH, minus epsilon CC, and minus epsilon CCl. So if we know these values from a table, then it is possible to determine this enthalpy, standard enthalpy change of this reaction, and the values are given here. This one, carbon-carbon double bond, 144.0 kilocalorie per mole, and plus this one 103.0 kilocalorie per mole, and minus, if we take this minus count, then this will be plus, and CH bond energy is 99.4 kilocalorie plus, and the carbon-carbon single bond 83.3.1, and carbon Cl bond 78.5. All are kilocalorie. So whenever this problem is solved, it will give you minus 18.0 kilocalorie. So this amount of the enthalpy change, standard enthalpy change for this reaction will give you minus 18.0 kilocalorie. And by the use of this bond energy, this value is to be calculated in this way. Similarly, the standard enthalpy of formations could also be determined by the use of this bond energy values. So bond energies will be very helpful to calculate the heat enthalpy changes of these different reactions, but this value will give more or less to some extent approximate, at the bond energy. If a bond energies are calculated in a very accurately, then this value will also be accurate. Now I like to discuss these two small things. One is the heat of enthalpy of neutralization. It is naturally the enthalpy change whenever 1 gram equivalent of this acid will be neutralized totally by 1 gram equivalent of this base. They are in aqueous solutions and giving this product salt and water. And these are in aqueous means they are in a sufficiently diluted solutions so that with addition of the solvent no further heat change occurs due to this dilution. And the standard enthalpy of this neutralization reaction is minus 13.7 kilocalorie. If we take another example, say nitric acid aqueous plus sodium hydroxide, and this is also aqueous, means they are in very dilute solutions, and we can get this product sodium nitrate and aqueous plus water in liquid. And it is surprising that the enthalpy, standard enthalpy of neutralization for this reaction also equal to minus 13.7 kilocalorie. In fact, any strong acid and strong base, whenever it is neutralized in dilute solutions, they will give identical values of this enthalpy of neutralization. But if we take one say HCl aqueous plus say ammonium hydroxide, this is also weak base. This is weak base, and giving this ammonium chloride aqueous plus water, in this case the heat change will be different, and delta H naught 298 Kelvin is found to be minus 12.8 kilocalorie, minus 12.3 kilocalorie. If we take another example, say acetic acid, it is also weak acid plus say it is base, strong base, and it is also aqueous, and giving this sodium acetate, it is in aqueous and plus water. In this case del H naught 298 Kelvin becomes equal to minus 12.6 kilocalorie. Another example I can also give, this hydrocyanic acid. Hydrocyanic acid in aqueous, very weak acid, and you can get this sodium hydroxide in aqueous and neutralized as sodium cyanide, and in aqueous plus water. In this case, since it is very weak, so the heat of neutralization delta H naught or standard enthalpy of this neutralization at 298 Kelvin equal to only minus 2.9 kilocalorie. So automatically the question comes, two questions are emerging of this data. One is that if we use this strong acid, strong base, then standard enthalpy of neutralization is fixed. But if any one or two both taken weak, then this standard enthalpy of neutralization is low, is less than the value minus 13.7. To search for this answer of these two questions, one is that for strong acid, say H, explanation for the data, explanation, Acnum 1, This is suppose strong acid plus suppose this BOH is aqueous strong base and giving the salt Ba aqueous and plus water liquid. In this case, as these two are the strong, this is also strong, all salts are strong. So it can be write as H plus plus A minus, and this one could be written as B plus plus OH minus, as they are completely dissociated in aqueous solutions. And this is also B plus plus A minus and plus water. Water is very weak electrolyte, and so this remains in this molecular form. If we cancel the terms of this chemical equations like the algebraic equations, then B plus and B plus cancels, A minus cancels, so it becomes only the H plus aqueous plus OH minus aqueous and giving this water liquid. Since in all the strong acid, strong base neutralization cases, this is the main reactions. 1 mole of hydrogen in aqueous solution, hydrogen ion in aqueous solution reacts with 1 mole of hydroxyl ions in aqueous solution, giving this 1 mole of water. Since initial state and final state reactants and products are same in all the case of strong acids and strong bases, so this delta H not 298 Kelvin also will be the same, and this 17.8 Kelvin. Then explanation, second application. Explanation. And second application is that if we take this one acid or one base with, then this will be less than this one. Why? Actually, a portion of this heat released due to the neutralization is used to dissociate this weak acid or weak base, and so from that value we can calculate the enthalpy of dissociation of this weak acid. So the enthalpy of this dissociation, so for this weak acid or weak base, if we take for this neutralization reaction, then actually the standard enthalpy of neutralization is found to be less than it is expected from this strong acid, strong base. So from that we can calculate the enthalpy, standard enthalpy of dissociation of this weak acid. Suppose this one, in this case, hydrocyanic acid. In case of this heat standard enthalpy of neutralization is found to be minus 2.9 kilocalorie. So actually the difference from this to this will give you the standard enthalpy of dissociation of this hydrocyanic acid, and this one standard enthalpy of dissociation of this HCl would be obtained this one minus this one, this one minus this one, minus this one, and will give this 10.8 kilocalorie per mole. Means 1 mole of hydrocyanic acid in dilute solution. If we like to dissociate, then this amount of heat will be required under the standard conditions. Now the last one. I shall discuss now the enthalpy of solution. It is the enthalpy change when 1 mole of this solute is dissolved in a specified amount of solvent. If the amount of the solvent becomes different, then the enthalpy change will also be different. And some solutes, when dissolved in a particular solvent, the heat is liberated, and in case of some substances, the heat is absorbed. Suppose if we take this sufficiently, whenever 1 mole of this solute is completely dissolved in sufficient amount of this solvent, so that no more heat change occurs by adding more solvent, then it is called the integral enthalpy of solutions, which is very commonly known as enthalpy of solution or heat of solution at constant pressure. So if we take one example, the HCl gas, this solute, and it is the, whenever dissolved, it is the exothermic, the heat is liberated, and when 10 moles of water is taken solvent, then for the 10 moles of water, this amount of kilocalorie per mole means water HCl, this solute have been taken 1 mole. So it is 16.5 kilocalorie. If 40 moles of water is added, then it will be minus 17.4 kilocalorie. If 50 moles of solvent water is added, then it is increasing 17.5, and if 2000 moles of water is added, then it is minus 17.7. If infinite amount of the solvent is added, water is added, then this value is minus 18.0, and this is the integral heat of solution. If we draw this graph, here the number of moles of water, and it is the standard enthalpy of solutions for HCl gas, then at the start, the starting point will be 0 when no water is added, and it is increasing with this addition of the water, number of moles of water, and it attains a steady value, and this is called the integral enthalpy of the solutions of this HCl gas. So this is all about this thermochemistry. Next class I will exclusively discuss the effect of temperature on this enthalpy of reactions, means the Kirchhoff equations, very elaborately, and also I shall state some problems. So thank you all for watching my video, and if you like this video, then it will be very helpful for you, and also for me it will encourage me to do more videos. Thank you all again.